All right, number 17, we want to evaluate the limits of this and provide a sketch. So this is f of x equals 5 plus ln, natural log of x. So this is one of our parent functions. If you recall, e to the x is this exponential growth function. It crosses at 0, 1. Natural log is the inverse. If you think about the dotted line y equals 1, this graph is a mirror image, and so it curves up and crosses and goes this way. And traditionally crosses at 1, 0. So if you flip-flop x and y. The only difference with the plus 5 is that this graph will get shifted up 5 units. So it'll still kind of hug the x-axis, but the whole shape of the graph will curve up and it'll go through this ordered pair 1, 5, because it got shifted up 5 units. So this is what the shape of the graph looks like. So from this just general shape, from what we know about parent functions and transformations, just shifting, we can determine the limit from the graph. So as x goes to positive infinity, this graph is going to be going toward positive infinity. It's tapering off, but it's going to continue to increase the further we go. So we would say it's going toward positive infinity. As we go toward 0 from the right, so I'm coming this way and going toward 0, this time it's going down, down, down to negative infinity. And so we just get both of those limits from the graph, looking at the end behavior. And then we pick out the one that looks like the graph of that, and so A looks the most like it. There's the vertical asymptote at 0. This graph is kind of like I want to say radicals. To me, you can't use negative numbers, so it looks like the square root, similar to the square root shape. Here we want to determine the end behavior of this transcendental function. So we have sine of 3x. Okay, so let's talk about trig functions. So if you've graphed trig functions, sine. A traditional sine graph, and we usually put our tick markers at every the easy 0, 1s of the unit circle. So we have 0 degrees, we have pi over 2, well, we're doing it in radians, we have pi, and then we have 3 pi over 2, and then we have 2 pi when we get back. So normally this is 0, and then we go pi half, and then we go pi, and we go 3 pi over 2, and then we go 2 pi. So the sine value is the y coordinate. So at 0, this is 1, 0. This goes out 1. This order pair would be 0, 1. This order pair would be negative 1, 0. And then this order pair would be 0, negative 1. Okay, so it's just kind of like going around the circle and hitting these points 1, negative 1, 0, 1. So when you're at pi half, which is here, sine has a value of 1. So we're going to say this is 1, this is negative 1. So we started at 0, we're at a value of 1. When we go to pi, the sine value comes back down to 0. And then when we go to 3 pi over 2, the y value is a -1. And then when we go back to 2 pi, we're back at y value of 0. And it'll just keep going around the circle and doing the same thing. So you get this like wave curve. So it just kind of oscillates. The difference is when you have a 3x, the amplitude, no. This is a compression. It'll just kind of divide the period. So instead of the period going through at 2 pi, it will be divided by this b value of 3, and so we'll have 2 pi divided by 3 will be our period. And then usually what we do is we will take this period and divide it into 4 chunks. So if you divide that by 4, that will be the same as multiplying the denominator by 4, and that'll give you 2 pi over 12, which is just pi over 6. So our periods would now be pi over 6, and I'm sorry, some of that's running off. So if I was to graph my new function on this same plane to see what happens, let's see how to do this. We would have a pi over 6, and then 2 pi over 6 would be pi over 3, which would be like here. And then 3 pi over 6 would be here. And then we have 4 pi over 6, which would be 3 pi over 2. No. 4 pi over 6 would be 2 pi over 3. So the same function would just be like a horizontal compression. So my first point would still be at 0, and then I would be at 1 here, and then back at 0 here, and then -1 here, and then back at 0 here. So same function, it just gets horizontally compressed. So it's going to be like oscillating between 0 and 1 much faster. So let me show you that with the graphing technology, and then as this graph goes to infinity, it's just going to continue to oscillate back and forth, and so we won't be reaching any finite value. We're not going to infinity or negative infinity. So we would just say that the limit does not exist because it's just oscillating between, it's alternating between 1 and -1. So let me see if I can show you that graphically just for fun. I'm going to go to y equal. We're going to just do sine of x. So this is going to be the parent function. And then we're going to go, I'll do the sine of 3x in just a minute. Let me go to my window. We're going to put this in terms of pi. So I'm going to say -2 pi. And we're going to go up to 2 pi. And we'll count by pi halves. This is a regular function, pi over 2. And then my y minimum, let's just say -2 to +2. And we'll count by 1s. So if I graph this, you'll see a pretty good image of the sine function. So this is just going through the first oscillation that I graphed here, stopping at 2 pi. Now when I graph on the same axis sine 3 pi, or sine of 3x, sorry, you'll see the new graph is just alternating a lot faster. Okay, so you can kind of see some of those same points. It goes up a little bit before, and it's down when we're at the maximum, and then it'll just keep oscillating. And of course I could change the period and let it count by pi over 6, and then it'll end perfectly there. But that's the general idea with graphing trig functions. So we will say the limit does not exist when we go to positive infinity and negative infinity, because it just continues to oscillate and it doesn't approach a finite number.